Dude, I cut my hair. It's crazy. You know what's good about this hair? I could say I cut my hair without actually cutting it because if I shower, it makes it look like it's shorter. This is so good. Amazing. But anyways, you guys are here to watch me practice because I need to actually start studying. Dude, it's literally on Monday. What am I doing? I have literally not started studying. Well, I mean, good time to put that usable skill to use. God dang it. Why did that can't? You know, we're not doing commentary now. Hello everybody. It is time to do some practice AP Physics C electricity and magnetism questions. Now we're doing 2018 because I already did 2019 on my own time, like a little bit before this. So let's get started. 45 minutes on the clock. Alrighty. Oh yes, a Gauss's law problem. This is gonna be epic. A solid plastic sphere of radius A. I'm dying. And a conducting spherical shell of inner radius B and outer radius C are shown in the figure above. The shell has unknown charge. The solid plastic sphere has a charge per unit volume given by rho r is beta r. Okay, where beta is positive constant, blah, blah, blah. Okay, express your answers, part A, B, and C. Okay, so a Gaussian sphere of radius r concentric with the plastic sphere. Describe the expression for the charge enclosed by a Gaussian sphere. So he just wants the charge enclosed. Okay, dude, I was practicing and I literally cannot read, so this time we're actually going to read the question properly. So basically you got a sphere and then your Gaussian surface is in here and you got A and there's R. So it says that it has a non-constant density. So whenever you have non-constant density, you have to integrate. And the way I like to think about it is you're adding a bunch of spherical shells. So you want to add this spherical shell. Let's say that we're integrating over x or something. Then if this radius is x over here, then the density is beta x. So that means that the overall charge of this thing is going to be beta x times 4 pi r x squared dx. Because this is the volume of the shell, this is the charge density. So we got to integrate beta x pi x squared dx, 4 pi x squared, 4 pi x squared. And then we do this from 0 to r. And then this should give us, it should be 4 pi b x to the 4th over 4, so this cancels out. And then we plug in our r and 0, and this gives us pi b r to the 4. Okay, now the next one should not be dependent on r because the amount of charge within it is not changing because you're just adding more open space. So in this case, we just have to find the total charge of the plastic sphere, which we just plug in a over here, and we basically get that our total charge is pi b a to the 4. Okay, and then b. So once the magnitude of electric field, then literally what we could do is just divide by 4 pi r squared in both cases. So for the first one, it would give us b r to the 4 r squared. It just literally gives b r squared over 4. And then the second one would be pi, or b a to the 4 over 4 r squared. Okay. And then C, at any point outside the conducting shell, it is observed that the magnitude of the electric field is 0. Determine the charge on the inner surface of the conducting shell, and determine the charge on the outer surface of the conducting shell. So essentially, for the electric field to be 0 within the conductor, because by definition the conductor has to have a 0 electric field, its inner surface must have the same charge, same but opposite charge as the inner sphere, right? So that it could completely cancel out the charge, and by Gauss law, our charge inside is going to be 0, so our electric field throughout the conductor is 0. But we also want it to have an electric field outside of the conductor of 0, so like the charge on the outer thing should not change anything, so it should also be 0. So this over here would be Q enclosed should be 0, so inner surface should have negative pi b a to the 4. And then for the other one, it's kind of the same thing. Q enclosed should still be 0, so should have 0. Okay, epic. D. On the axis below, sketch the electric field as a function of the distance r from the center of the sphere. So we know that it's like r squared before a, so like that, and then it goes to a, at which point it starts falling off with inverse square law. So it's like kind of like that, and then it reaches to b, at which point it just drops to 0 immediately. Alright, epic. Figure below shows the sphere and the shell with 4 points labeled W, X, Y, and Z. Point W is at the center of the sphere, point X is on the surface of the sphere. Okay, and blah blah. Okay, rank the following points according to their electric potential at that point. So electric potential is the negative integral of the electric field over distance. So you can think about it this way, right? Like W is going to have the highest potential because our electric field is positive everywhere. So as we go out, our voltage is going to get more and more negative because we're taking the negative integral of a positive thing. So it starts high at W, so W is 1, then X is a bit lower, then Y is even lower, but then Z is the same as Y, so just 3. Another way you could think about it is like if you put a charge at W, it has a positive charge at W, so it's gonna push that charge out, and then it's still gonna have a positive charge all within it, so it's gonna keep pushing it out until it gets to the outside of the Y, and then there'll be no force on it, but it'll keep going up. So this should be fine. Is that it for this question? Epic. So let's check our answers. All right. Pi b over 4, 8, okay, epic. Oops, I forgot my epsilons, god dang it. Epsilon 0, okay. And then this is right, and that's right, okay. That's also right. And then 1, 2, 3, 3. Epic! Okay, let's move on to the next question. Did I even start the timer? Yes, I did. Oh, that was pretty fast. Okay. Dude, Gauss is my guy, okay? I've done so many Gauss's law problems, it's not even funny. Okay, an experiment designed to measure the dielectric constant of paper has an area of 0.060 meters squared. Using an aluminum foil, the two parallel plates are created with the same area of the paper. 500 sheets of paper are placed between the aluminum foil plates to create a parallel plate capacitor as shown. Okay, using a multimeter, the capacitance of the capacitor is measured. The number of sheets and the total thickness D of it, okay. And you reduce the number of sheets of paper each time. Indicate below which of the quantities should be graphed to yield a straight line whose slope could be used to calculate the numerical value of the dielectric constant of the paper. So, we know that our capacitance, C, is equal to epsilon 0 A over D, and if you have a dielectric, it becomes K. So, our D is changing, so we want to find the dielectric constant. So, it's basically like Y is equal to mx, and our y could equal c, and then our x could equal 1 over d. Or it could be ka over d, but it's just that you could use the slope, so I'm just going to go with 1 over d because that makes sense. And on the actual test, I would label the column 1 over d, 1 over meters, and then I would calculate it out. Okay, and then you plot it. I don't feel like plotting it. Or actually, should I just do it? Let's do it. Okay, so what are our d values? Let's see. Alright, so we need to take 1 over d for all of these d. So 1 over 0.045 is 22.2. Okay, and then 1 over 0.036, 27.8, and then 1 over 0.027, 37.0, 1 over 0.018, 55.6, and then 1 over 0.01, which should just be 100. 100, okay. So now we gotta graph this, boys. So we have 6 to 21 on the x-axis, no, on the y-axis. So C farads, and then 1 over d in 1 over meters, and we got 2. Let's see. We'll go from 0 to 25 maybe. So this will be 20, 15, 10, 5. And then over here, our 1 over d goes from, let's go to 100, so this, 80, 60, 40, 20. And then 22 and 6.5. Just pretend I put times 10 to the negative 11 in there, okay? Don't worry. And then 22.2 goes to 6.5, somewhere around there. 27 goes to like 7.4. So 37 goes to 8.9. 11.9 is 55. Okay, right there. And then the last one, 100, just goes all the way to 21. Epic! Okay, so we have kind of a line. I don't know if I could draw it straight, but it looks like it just goes like through this guy. So if we wanted the slope, we would take this guy, which is going to be 55.6 on the x-axis, and 11.9 times 10 to the negative 11 on the other one. So we'll just divide these to get the slope. 11.9 times 10 to the negative 11 over 55.6. And that gives us 2.14 times 10 to the negative 12. Alright. And do we have units for that? Oh, no, it's just a ratio. Okay. Oh, no, that's not our final dielectric constant. We need epsilon 0. We have to divide by k and a. So, we have to divide by epsilon and a. So, a is just going to be 0.06, and then epsilon is going to be 8.85 times 10 to the negative 12, right? I think so. Hey, let's go. We remember our stuff. That's pretty good. Over 8.85 over 10 to the negative 12 over 0.06. And we get 4.03. Oh, that sounds pretty good. 4.03. Should have known something was off when I got a negative 12. How much time do we have? Oh, okay, that's pretty good. Okay, so a student now makes a capacitor using the same aluminum foil plate and does one sheet of paper. God dang it, dude. Using the experimentally determined, okay. Oh, good. So we know how to calculate the capacitance. Epic. He uses uncharged to build a circuit using a wire. 30, okay. Calculate the current in the battery immediately after the switch is closed. So that is like as if the capacitor did not exist. So this would be a 40 ohm resistor and then plus 80, so 120. So we would have V over R, which is 36 over 120, which is 3 over 10, which is 0.3 amps. Okay, epic. E, determine the time constant. That's really just the other two resistors. So that's like 40 plus, so 120, and then you have to multiply by C. So it'd be 120 times 18 times 10 to the negative 9. That is equal to what? 2.16 times 10 to the negative 6. And then it should just be seconds, okay? I think real algebra does not include units, right? Likely we should just do it anyways, okay. Student A and B measure the time it takes after the switch is closed for the voltage, okay? And they find that it's longer than expected. So if the capacitance value is correct, then the resistance means that, okay, so the time constant is how long it takes. So if the time constant is bigger, then it would take longer. So the fact that it takes longer means that the time constant is too big. Or no, our time constant that we calculated is too small. The time constant that we calculated is too small, so that means our resistance value is too small. Wait, what? Oh, the actual resistance value. So it should be larger because we want a bigger time constant, so larger than measure. And then student B assumes that the resistance is correct. Same thing, it's larger because the time constant is RC. Experimentally, what would account for it? Like internal resistance of the battery, like resistance of the wires, all that good stuff. For the other one, why would the capacitance be larger? I mean, there might be air or something, right? Well, what else would it be? Yeah, there might be air pockets in the paper, right? Yeah, that's probably what it's looking for. Okay, let's see. Okay, that's what I said. Okay, I'll pretend like I plotted the data. Should be, okay, so we're approximately right. That should be fine. 0.3, 2.16 microseconds, with the same thing. Okay, good. What? Okay, sure. I guess I would lose this 1 point, but that's fine. Okay, last question. Let's do this. Alright, so figures above represent different views of two long, straight, horizontal wires 1 and 2 carrying currents I1 and I2. The direction shown. The wires are held in place. In figure 1, the current is directed out of the page, and wire 1 is the distance D above wire 2. Point P is the horizontal, okay, blah, blah, blah. And distance D directly above, okay. Express your answers to A and B in terms of ID and, okay. So we gotta use Amperes Law, very fun. So Amperes Law basically says that mu 0 I is equal to integral, closed integral of B dot dl. And basically what this says is you multiply the length of the loop by the magnetic field if it's a constant magnetic field, which it is. So, because it's a wire and it's symmetrical, so it's just going to be 2 pi r, which is d, 2 pi d, b. So our b is just going to be equal to mu 0 I, it's asking for the, yeah, so over 2 pi d, epic. And then there's A, B, net magnetic field. So we also had to include wire 1, or wire 2. So wire 2 should just be the same thing, except it's going into the page. And then wire 1 is going upward. So it should be into the page and upward. So it should just be, but the magnitude is the same because it's the same distance from both wires. So we just multiply by root 2 because it's like 1 plus 2. And then it gives you root 2 of that. So it should be mu 0 I over root 2 pi d. Okay, C. Calculate the numerical angle to the horizontal for the direction of the, it should just be 45 degrees as we found. 45 degrees. D. Wire 1 is now released. What is the following best describes the initial motion of wire 1 due to the magnetic field of wire 2? So the field is going to be parallel. Wait, what? Yeah, so the magnetic field caused by wire 2 is going to be the opposite direction of the current, but it's still parallel, so that's not going to move. Okay, so we can just justify it using the fact that the magnetic field due to wire 2 is going to be parallel to the wire. Oh, but it starts aiming downward, so it'll be I, and then slightly downward because it's like a circle. Wait, sorry. So wire 2 is into the page, right? But it starts curving down, but it also starts curving down. Okay, so if it's curving down, okay, let's think. So let's say this is wire 1, and the magnetic field starts curving down here. It's like this, like this. Okay, so over here, our current is going this way, right? Yeah, our current's going this way, and then, so for this one, it's I cross B, so it'll be coming out of the page. This force over here is coming out of the page, and then I cross B is going into the page over here. So that means it'll rotate this way, so in figure 2. So this side is getting pushed this way, and this side is getting pushed this way. Wait, what? So if we rotate it this, yeah, like this. So this is getting, so rotate clockwise. Okay, makes sense. Is there any more? Okay, so wire 1 is now replaced by a conducting rectangular loop. Okay, loop is placed in D, and then the current is decreased linearly. I do not know if I have space, but basically you want to integrate from closer to higher, right? Because at any distance from the wire, the magnetic field is all the same. So, but by Amperes law, your magnetic field is going to be, well, if r is the distance, or what is r? Yeah, r is the distance, so it should just be mu 0 I2 over 2 pi, this should be I1, mu 0 I2 over 2 pi d, or r, 2 pi r, and then we want to integrate this from, yeah, we literally just want to integrate it, right? And I2, we just plug in that, so should be fine. And we want to multiply by L times dr. Okay, so this one looks right. Yeah, that seems fine, so it's this one. Okay, given that the flux is given by this, derive an expression for the magnitude of the current, if any, induced in the loop. So basically what you want to do is you want to take the derivative of this. Yeah, so a negative change in the flux. Alright, so we got to take a derivative of this nasty thing. Well, this is a constant, so that doesn't change. And then, oh, that's pretty easy actually. So the only thing is a t, right? So that's the only variable. So mu 0 I 0 L k. And we had to take the negative, so that negative gets canceled out over pi ln d plus w over d. Okay, that is our answer to F. And then G, what is the direction of current, if any, induced in the loop seen in figure 3? So it's like this, it's going this way, but it's reduced. So that means it's as if it's increasing this way, so the flux should be, flip it, and now it's clockwise. Alright, so basically the way I like to do it is like, it's going into the page, right? That is the direction in which the flux is originally. But it's decreasing, so it's increasing out of the page. So you would think that it's counterclockwise, right? Because it's increasing this way, so by the right hand rule, it's going counterclockwise. But you gotta flip it because of the negative sign, so it's clockwise. Epic. Let us check our answers. Alright, that's what we got. Wait a minute. Oh, I can't read. God dang it. Wait for it. I forgot. So I1 is just I, and then I2 is, so it'd be 2 in one direction, and then, wait. So I2 exerts a twice as strong force into the page, so this would be twice as much force, and then this would be 1 times as much force, so it'd be root 5 over here, over 2. Or no, is that right? Yeah, it should just be root 5. Oh yeah, but there is a 2 from over here. Okay. And then this, on the other hand, will be like tan inverse of 1 over 2 in degrees times 180 over pi for 26.56. 26.6 degrees, okay. And we didn't screw up anything else. I think we're good. Okay. Alright. Which one is it? Which one is it supposed to be? It says, yeah, now clockwise starts. Epic. Okay. And then it's this one. Okay. That's what we said. Yes, that is. Oh, where did the R come from? Oh, did I just miss an R? Oh, it's asking for the current. This is the EMF. So yeah, we'd have to divide. Okay. So would I lose points for that? I guess I would lose points for that. Okay, I got the EMF right, so that'd be 1 point, but then I would lose. Okay. And then clockwise, very cool. Alright, we made it through. How much time do we have left? 15 minutes? That's not even bad. Epic. Alrighty, thank you guys for watching. Hope this was helpful. Let me know if you guys want more of these videos. I was just practicing. I didn't make as many sillies as last time, but I still cannot read. I just need to practice reading questions. This is so triggering. But anyways, as always, if you enjoyed the video, leave a like and subscribe for more. Thank you guys for watching. See you guys next time.